What I want to do today is, so hopefully I had time to read this. This is from a poem. The poem, actually, the entire poem is very interesting, but it's about how the world changes. And the message of this quote from the poem is that we should never complain that things are changing. We should only complain if things don't change. And in fact, if you think about it, if things were stationary and never changing, this would be a very dull existence. And this talk is really all about change. So we're gonna talk about time travel, and you'll see what I mean there. But the message I'm gonna actually show you is this time traveler really missed a lot, because as you know, time travel, you are in one point and then you jump, and so you miss all the excitement of history. And the excitement of history then in networking is what I'm going to talk about. And what I'm going to show you is basically the evolution of the internet and basically trying to predict this and project this into the future. So, let me also say that this is not about my research. I have research in areas of currently of mobile cloud computing, network virtualization, and adaptive video streaming. I'm here for a couple of days. I'll be here, in fact, tomorrow at the university, and happy to talk to people if they have interest in these areas. Okay, so moving right along. So, as you know, if you're a movie fan, from a while back, but the movie I imagine is still very popular. You know, time travel, of course, is popular, and we have this time traveler. This time, it's a networking researcher. This is I can actually do this if you want to know. I can tell you. But so this time traveler left the world in '85 and showed up immediately today at June 4th at 3 p.m. And this time traveler now happens to be a networking researcher. And let's see what he saw. So he's interested, obviously a lot of things have changed, but he's interested in networking. And so what he saw was that in 85 and 2018, I picked 85, by the way, because this is the year I finished my PhD, so it sounded like a good time to travel from. So if you look at what we call today the internet in 85, this is what it looked like. This is actually a part of what's called the NSF net backbone. This actually happened after what people know as the ARPANET, and when things became commercial, and it's just like 6 nodes. Today, actually, the internet is very hard to visualize, very hard to draw a picture of the internet. The best visualization, this is a graph from 2014, but they have pictures that even more crowded, even harder to see. But this is a visualization of what the internet looks like today. This is a very complicated graph. The graph has about 70,000 nodes. Each of these nodes is actually not an individual network node, but a network. And each network then is made up of multiple nodes. So this is close to about 700,000 to a million nodes like this one. So we've seen an explosion of scale, basically. And when you see it like this from one point to the other, you appreciate what has happened. I give this talk at multiple locations, so I like to give people, I don't know how many people are locals, but I like to give people a visualization of what happened to where you are in this time frame. This is, I found, easy to find pictures of Helsinki in, this actually probably is older from the looks of the cars. Doesn't look like 85, looks like a little bit older. But actually, surprisingly, this is what it looks like today. Not a whole lot of, the buildings on the side, the cars have changed. Of course, the street cars are very different, but the cobblestone here is the same. But anyway, everything has seen considerable change, including Helsinki and other localities, I'm sure. Okay, so let's look at the other things that we were doing for the network. So network applications. In '85, the higher tech application was file transfer. This was, for me, one thing, and I said, you can really do that, which is move a file from one computer to another. And it was relatively straightforward. The interface was a bit complicated. You had to log in and so on, but it actually almost felt like magic that we are able to do this. Today, of course, we do a lot of other things on the network. Video streaming is a very popular application, and social networks and all. So the network actually has seen an explosion in what we use it for. One of the biggest uses of the internet today is content distribution. And I'm often asked about whether content distribution is really an internet phenomena or it existed before. And actually, there was in '85, there was efforts at what we call today digital content distribution. Obviously, there are always newspapers and TV stations, but all of that is more analog. But digital content distribution looked like this in the mid to late '80s. These are systems that were called teletext that you would display on your TV. The graphics, of course, are pretty rough, but actually you could do a bunch of things, including, do travel guides, listen to the radio, do weather forecasts, and actually, if you can read this is tele software. And BBC was selling computers that then you could connect to the cable. This was not really the internet as we know it today, and actually download software off the network onto your computer through this tele software system. So a lot of the things that we're familiar with were there already. People had thought of them and thought, wouldn't it be nice to be able to do it, even before the internet. Of course, when the internet came, we continued to be able to do this, but we are able to do it now with significant quality, and of course other technologies have improved other than communications. I'm going to now take a little bit of digression to talk about how networking people used to do research. And even if your area is networking, you'll really appreciate this. But even if it's not, I think I've seen it in a lot of computer science subdisciplines. At some point, networking people thought, and I remember, vividly being a graduate student thinking that that's what I was doing. As with any engineer building an artifact and designing an artifact, what you thought you were going to do was design it and maybe have some formal design principles. And then once it's designed, you build it. And then once you built it, you are done, right? I mean, you can then tweak it a little bit, but then you sit back and enjoy it. And in fact, if you look at the old literature, what you will see is this kind of thinking. And this is a very old paper, again, from the 80s, written by, Bob Gallagher. If people are in information theory, they know him. He's one of the most respected authorities in the early days of information theory, and one of his PhD students. And it was about networking, this is too small maybe, flow control and routing algorithms for data networks. So all about writing equations, the formalism, and the idea was we're going to use these equations to actually understand how to design networks, and then we're going to use them to build them. What happened, again, fast forwarding, there's a lot of steps along the way, but as we look at it today, it's actually almost feels, it depends on your point of view, but it could feel like a nightmare because this is what's happening. We did a bit of design, but people never believed anything you designed until you built it. So once you built it, though, it obviously wasn't working and there had issues, and the only way to understand it was to measure it. And once you measured it, then you understand what was wrong with it, and then you fix it, and then you keep repeating this forever and ever and ever and ever, right? And so this is really how networks live today. There is no such thing as a network that is stuck in whatever particular design that is not continuously being changed to adapt to things, adapt to technology, adapt to applications. I just picked a paper from a Google group that talks about yet another way to do transport when you thought, for example, transport in the internet was pretty stuck. They come up with a different way of doing it. So this is another thing that is interesting. If you look at this, at old conferences, this is again SIGCOMM, ACM SIGCOMM, which is the most well-known conference in networking. In fact, was in Helsinki not too long ago. In '85, they published 22 papers, but this is the most interesting thing. The number of authors per paper was 1.9 on average. So on average, around 2 authors per paper. The minimum was 1, lots and lots of papers with single authors. The maximum was 3. The most number of authors per paper in SIGCOMM 85 was 3 authors. And again, if you look at the titles, you will see this mindset that we're building something, we're designing something to build. These are window and flow control, are topics that people still don't understand, are still working. Fast forward, and SIGCOMM 2018 hasn't happened yet, so this is 2017. There are more papers, but it's interesting. The average authors per paper was 6.3. So clearly an explosion. There's no more this tradition of single author papers. There are actually no single author papers. Actually, it'd be crazy to try to think that you could write a paper that would be accepted at SIGCOMM just by yourself. Never could happen. The minimum was 2, but in fact, this was an outlier. I've done these statistics for a number of years. This probably was the first time in like 5 years where a paper had 2 authors only. The maximum was 24. There was a paper with 24 authors. If you think about it, paper is 12 pages, you have 24 authors, each of us writes half a page. That sounds like a sweet deal. You know, I can write half a page and we staple it together. Obviously, that's not how people do it. But the other thing, of course, is that, you know, these very dry titles don't work anymore. You have to always give your paper some interesting name, so people remember it, because there's so much going on. So this is taking the edge off with espresso. I mean, this is just regular coffee, unfortunately. But anyway, every paper now has to have this cute name that people will remember, and cute title, and then you tell them what it was. Actually, even if you read this, you don't quite understand what it is. Anyway, so I mean, if you read this title, you understand exactly what they were doing. They were doing window selection. This is not clear what they're doing. Okay. My research, and it kind of tracks, so I don't ever want to sound like I'm blaming people. I mean, I lived through this and I did exactly the same thing. So this is probably one of the first papers I wrote as a faculty member, and yes, I looked like this. It was a single author paper. There was a lot of math and equations, and in fact, if you ask me today to explain this to you, I cannot. It's so long ago, and today, of course, I never got into the 24 author paper, but I've done 6, 7 author papers. This is a paper that we wrote for Mobisys with people at AT&T. Okay, so this is just the run through this time traveler. The interesting thing, though, that I want to show you is that what happened in between is actually quite interesting, and you really never wanted to make that jump, because you lose a lot of context and you lose a lot of understanding of how evolution takes place. And this is really what I want to talk to you about. But a few caveats, first of all. This is about history, and I'm not really writing history or rewriting history. There's a lot of good histories of the internet written out there. All I want to do is add structure to it. So, obviously we'll talk about the history, but I'm more interested in the structure and whether there are patterns that we can come up with from this history. The second thing is, I'm really, other than the one paper that you saw, I'm not really going to talk about my research at all in this, and it's not a step through all the research that I've done during my career. The other thing is, I'm going to be critical at some point, but you all understand that looking back is easy, and so that's what I'm doing. I think going through it is very hard to understand what's going on. So I have that advantage of being able to look back at this point. I actually ended up writing a paper. This is a talk that's been developed for a few years, maybe a couple of years. And I wrote a paper over last summer, and it's in ACM, the SIGCOMM CCR, Computer Communications Review, appeared in the January 2018 issue. So if you want some more detail and actually good citations and all that, it's there. Okay, so I'm going to actually tell you this in 3 parts. The first part I'm going to talk about is, we all heard this expression, necessity is the mother of invention, right? That's, and I'm going to try to explain to you what this means for networking people and how that has translated into an evolutionary model that I think is very, very accurate in terms of predicting things. Then I'm going to have 2 chapters, and the first one is, and I don't speak Latin. I had to learn a few words for this, but basically what I'm going to call the consolidation phase. In the US, I wouldn't have to explain this. You understand this is on all our US currency. It's basically from many one. This is the motto of how the states got together to make one country. Okay, but this actually happened in networking as well. There were many networks, as I will show you, and they got consolidated, and for some good reason. Today, though, I'm seeing, and this is so 1 and 2 are really about the past, and no one really will argue about that. Maybe my models can be argued with, but basically what happened has happened. What I'm gonna predict, though, is that we're gonna see the opposite of this consolidation of many networks into one. We're gonna see, and this is ex uno pluria is actually the Latin way of saying from one many. Okay, thanks to Google Translate. Okay. All right. So, and also, I believe that I should give you the message. So now, you can maybe see elements of it, and I'll repeat this at the end. Basically, there are 3 messages that I want to get across. First of all, that if you look at how things have developed in networking, there is actually a fundamental process that underlies all the development. Okay. The second thing is that what we have today is just a product of this process. But it's a local minimum, if you will. Basically, we reached a point that may have, other things have developed over time. We would not have reached this kind of equilibrium. Would have been a different kind of equilibrium. And I don't believe there's anything fundamental about where we are today in networking, right? I mean, I think people will argue that the internet has been, the architecture and the structure of the networking today is kind of a preordained thing. Couldn't have happened any other way. I actually don't believe this. I mean, there could have been many ways it could have happened. We are certainly at a stable point, equilibrium, but it's a local one. And we could have been in any other one had history kind of developed a little bit differently. And that current state is basically we have a single, essentially, network that we all call the internet that delivers pretty much all of our services. What I'm going to argue is as we move forward, this paradigm is going to be shifting, that we're going to be changing from this single network to a many networks world, which is something we used to have at some point. And I'm going to argue for that. And I'm going to say that this is a good thing. This is not something actually bad. I think many networks is very good for networking research, and I'll explain that. Okay, so let's start with the chapter. The first chapter is basically about this necessity is the mother of invention. So the question is, what does it mean for networking researchers to say this? And so I'm going to translate. Necessity is basically, if you think about a service or application that you want to run over a network, that is what drives you. This is the thing that drives innovation. Invention in this case is networking innovation, infrastructure deployment. Okay, so we can restate this to say the following, that service or scale support, this is the necessary thing that we need, motivates infrastructure deployment. But notice I said 2 things. One is a new service, and the other one is the scale of the service. So when I teach my networking class, undergraduate networking class, which is about 15 weeks, the first week, which is about 3 hours, I actually show them how to build a network with 2 machines. So take one machine, put a wire to the other machine, and run a network, and you can do anything you want between these 2 machines. And basically we're done. It's actually a very simple thing. And then I tell them the rest, the 14 weeks that are left in class are about how to do this, but at scale. So scale is really the more interesting piece of the puzzle. It's not really that we're doing communication or networking, it's the fact that we're doing it at scale. So scale is another thing that has driven networks. We built small networks, they got larger and larger and larger. And as the scale has exploded, we have had to think, basically the necessity is the scale. We've had to invent new ways to do the infrastructure. So taking this and actually trying to visualize it, it's going to look like this. So if you think about it, there is a network service or some kind of scale that you want to achieve, and you take that and you build a network to achieve it. Okay? Except what has been happening to us is the service and the scale keep increasing. I mean, everyone knows, for example, that the network, when it was first built, was really designed around remote computer access. So basically, the internet was built to allow people in the US, and I'm sure in Europe, there were like 3 or 4 computers the whole country or in the whole continent. And people that didn't have a computer nearby needed to access it. So we built a network to let them get to that computer. And that was what it was for. And so we built this network to do the remote computing. But then we discovered, hey, email is the important thing. So we fixed the network, and this email now required us to do something different. And as we continue to discover new services, we have modified the infrastructure and redeployed infrastructure to achieve these new services. So this basically I'm going to call the service infrastructure cycle. So the service drives infrastructure, which then leads us to thinking about new services, which drives new infrastructure, and so on and so forth. Okay? And this is how the network became what it is now, is that many iterations of this cycle for about 40, 50 years. Scale is an important thing, like I said. So what scale means basically is the ability to handle large populations. It is the main driving force of networking and will continue to be the main driving force. Even today, we have a lot of people connected to networks. There are a lot of people that are not. And then there are additional devices. Used to be if you had one device per human on the planet, that was already too much. We're now talking about everyone having 3 or 4 devices, all network connected, plus all the sensing and all that's going on. So we have a lot of scale that is still ahead of us. We are not really, have not plateaued at all. The prediction today is about 20 to 40 billion in 2020, which is only a couple of years from now. We already are at about 10, 15 billion. Over the years, actually, it's interesting to see this. I've done some research on this, and this is a little bit maybe U.S.-centric, but so forgive me for that. But basically, I found them numbers from 1998. John Glenn was a senator, but he was 75 years old. He went up on the shuttle, so that was a newsworthy event. CNN broadcast the shuttle launch live, and they were getting 500,000 hits per minute for people to watch that video. Then about in the year 2000, a couple of years later, MSN tried to broadcast a Madonna concert. I don't know how many people actually know who Madonna is in these kinds of audiences. Google it, that's all I can say. But she was and in 2000 you wouldn't have had to ask this, and a concert by her online would have been very popular. The claim is 9 million tried to log in, but the idea, if you look at the news, you'll see that many of them just could not watch it because CNN was not equipped to handle 9 million users logging in 2000. And so there were quotes like this, "My nerves were broken down." More recently, though, this has been a successful one. In 2014, World Cup soccer was broadcast online, and 1.8 million unique users watched it. This is actually a better metric of how many 112 million minutes of video were delivered. More recently, this is again the National Football League in the US, was broadcast live. A game in London, in fact, was broadcast live on Yahoo, and they had 15.2 million users, unique users with 4 times as many million minutes, 460 million minutes. So what you're seeing here is the kind of the progression of scale. Basically, as time goes by, and in fact, you can go basically almost an order of magnitude here in a couple of years in terms of the requirements for scale. Okay, so this cycle that we saw, that the service infrastructure cycle was humming along, working really well, until in 2015, people started talking about this. They were complaining about, let me read this quote, the inability of the internet architecture to adapt to new pressures and requirements. So, and this was called the Internet Ossification. So basically this came from networking researchers that wanted to do new things on the network but just couldn't. And you know the saying, you can't teach an old dog new tricks. And this is basically what it is. The internet was getting old, and you couldn't actually make it do new things easily, okay? And there was lots of publications. This is from John Turner's group, well-known networking researcher, that talks about how alternations to the internet architecture were becoming very difficult, okay?
So what does this mean? So in the context of this picture that I showed you, basically the cycle that where you have new applications and new server and new infrastructure to support them, basically what we are seeing is this, that basically the cycle is stuck. We can now we can continue to think about new things and bigger scale, but we're not able to build the infrastructure to deploy that. Okay, so this is what ossification means in the context of this model that of internet evolution. So we'll come back to this in a little bit to see what happened, what is the solution. But what I want to argue first is that this cycle is really fundamental. That this cycle, if you followed it historically, things worked out really well. And I'm going to show you ossification in play as well. I'm going to talk about two kinds of routing. If you're not a networking person, don't worry. Unicast routing is when we send data on the network, we send it to only a single user. And that's normally how internet operates today. You send the email, you send the video, whatever, from one location to another on the network. Multicast is when you send something from a single user to multiple users at the same time. Right? So in fact, that's exactly what I'm doing now. I'm speaking, and you're all hearing me. I'm speaking only once, but many people are hearing me at the same time. That's a form of multicast. We actually use that. It's not very exotic. We do it when you send an email to a group or to multiple recipients, you're doing multicast. If you're watching live video or whatever on the internet, you're actually a recipient of a multicast because the video is coming only once and being distributed in the network. The thing today, though, is that multicast is achieved, so if I send an email to multiple people, actually the system is delivering a separate email to every single user. Okay, so it's not very efficiently done. Okay, so let me talk a little bit about internet unicast routing. So unicast routing, basically, I'm going to show you developments here. The detail actually is not really that important. What is important is to track the changes over time. So this is a graph of, on the x-axis we have the year, on the y-axis we have the number of users connected to the internet. It goes only to 2015, but that's as far as we need it. There are a couple of survey methodologies that were used. You see new survey, old survey, and this is the source of this graph, okay? But it's a pretty accurate graph. So now I'm going to track routing, which is from one user to a single user. In fact, there was a lot of stuff that happened even before 1969, because as you might imagine, this is a very fundamental operation of the network. If you can't do that, you can't do anything. So this was very early on, a paper by Prosser that describes all the different ways you could do it, although the network was not there. Then in the very early years of networking, there was something called distance vector routing. It's a form of routing that worked very well on very small networks. As the network got larger, distance vector routing could not work anymore, and we started seeing another form of routing called link state routing. Again, it's able to handle larger scale. But this was in the 70s, but this kind of scale cannot handle even the big really scale, the really big scale that we have today in the internet. So we started thinking about these hierarchical networks and building protocols to support routing there. EGP is exterior gateway protocol. It's a form of routing that handles these very large networks. But even that was challenged. And as the scale got bigger and bigger, we started developing different versions of something called border gateway protocol, and that was supposed to handle even larger scale networks. What you will see is border gateway protocol went through several variations. We're now in the internet today running BGP4, but BGP4 is really from the 2001, 2003 kind of time frame. Since then, nothing has happened. Okay, and if you remember, the ossification was around 2005. So basically, even though today we know BGP has problems, one of them is addressing scale, one of them is addressing security. There are proposals in place to do secure BGP, to do even better handling of what's called policy routing, which is what BGP does. But yet, there isn't a wide-scale deployment of any of these. And that's all because of ossification. So you can think of the cycle kind of running in iterations as the scale increased. And then at some point, we can think of, we want to do more, but we're stuck. We can't do anymore. Okay? The other thing, because to distinguish this from the next thing, is all of these have actually been deployed. So when I say EGP wasn't on paper, it was actually deployed in the network and was run for many years before BGP started coming into play. So there was a lot of experience with all these deployments. And in fact, when you look at the BGP standard, you will see this sentence at the beginning. This BGP was built on experience gained with EGP, as defined, whatever, and usage in NSF-net backbone, right? So all of these protocols were built on the deployment experience and the usage experience of the protocol before it. Okay. Now, let's look at multicast. So multicast, like I said, is the act of sending data from one user to multiple users. What you really ideally would like is for the network to support this. So what I mean is this. This is a network, trivial network. This is, if you want to send the same data to 3 people, this is how you would send it today. If you just can send only to one user at a time, you will send it, and there's a lot of duplication in the network. To do it efficiently, you want the network to do this. You want the network nodes or the routers to do data copying, and this is the most efficient way to do multicast. The problem, though, is that in order to do this, you have to change the software in the routers themselves to actually be able to do this data copying and efficient distribution. And people recognize this from way back. And however, today we don't have widespread deployment for that. And the reason I will argue is this did not track the cycle. And I'll give you an example. So this is the same graph I showed you before, but now I'm showing you multicast kind of progression over time. Multicast didn't come in very early in the network. The earliest piece of work you can find is on a paper by Dalal and Metcalfe. This is, by the way, if you're a networking geek, Metcalfe and Boggs are the people that invented Ethernet. So this is the same Metcalfe that invented Ethernet. He also has one of the seminal papers in multicast routing. Back in '78, notice the network had 100 hosts, very tiny, okay? But this was very hypothetical. He said, wouldn't it be nice if we did this, and here's how to do it. A few years later, Lorenzo Aguilar, who I actually don't know what happened to him, in 1984 wrote a paper in SIGCOMM and said, here is how to do it with the current internet protocol, the IP protocol. The problem was, with his technique, you could only reach 10 people. You could not multicast to more than 10 people. The internet people looked at this and said, we hypothesize a network that is this big. So it's only sent to 10 people is not good enough. And so as a result, this was never deployed. Okay, if people had done the same when they were thinking about unicast routing, nothing would have been deployed because none of these early protocols worked on the large network. But here, for some reason, they decided because this doesn't work on a large network, we're not going to actually deploy it. And because it was not deployed, no one really gained any experience. There were no debugging, no understanding of applications, nothing. Okay. Over the years, though, people started thinking of different ways to handle the scale, and they came up with other techniques, one that handles large groups. Again, the detail here is not important. There is, finally, though, after many years of doing things, I skipped over a bunch of things, a protocol called PIM-SSM, Protocol Independent Multicast, Single Source Multicast. Okay, not really important, but basically, at this point, everyone agreed this is the right way to do it. Okay, the problem is, this was all on paper and in the lab. There was no deployment in the wild, in the network, and there was no experience with previous deployments. So people looked at it and said, we're not going to do it, but also, this, if you look at the timing, this was around the time the network got ossified. Basically, it was very difficult to do this, even if you wanted to. So this never really saw deployment. So the argument I want to make here is the following, that basically, before ossification, the cycle was really helpful to get us moving into where we are now. However, if you followed the cycle and let things be deployed and tested and then improved on and tested and so on, you were doing really well. If you ever did not follow the cycle, like with multicast, things failed and we don't actually have anything to show for it today. Finally, the cycle basically today is inoperable. It's not relevant anymore because of ossification. So we can't talk about things cycling through improvements that address scale or address new services. Okay, so this is the chapter 1 about the model of the cycle and evolution. So now I want to show you that basically what the cycle led us to is this single network, okay? This is my icon here. So we had many tools at some point, and now we have one tool to do everything, okay? And evidence of this, again, people, networking people, we forget about history, including myself. And actually, so I dug up this textbook I have on my shelves from Misha Schwartz called Communication Networks, was published in '87. And if you go through this, you will see basically a lot of interesting things to see. But one of them is that you'll see chapters about all the different kinds of networks, right? I'm listing here a subset. TimeNet was a public network in the US. Transpac was a French network. DataPack was a Canadian public network. ARPANET was a US network, is only for research. And then there were all these company-built networks by Burroughs, IBM, and Digital. And in fact, the book had a description of each network and all of the technologies they deployed, and they were quite different. As a user, I remember actually having many networks. I had a network at work. And then I used America Online, which was a public, subscription service to get access to content. And then, if you wanted to run experiments, you went on the ARPANET and ran experiments. So we had different networks that we were using for different things. Today, though, we have one network. And like I said, I want to argue that this is not it's a local minimum that we have that does everything. But it's not really, we shouldn't really take it for granted. It may not have been the obvious thing to happen at any point. And we also underappreciate it. As we talk about networks, we underappreciate the fact that this has actually happened and is forcing our hand today to do various things. If you think about it, though, it makes sense for a number of reasons. One of them is that in the old networking world, connectivity was the main goal. The goal was not to give you services. The goal was to give you bit pipes from here to there. And if, it's like building a highway network. I want to get my car from here to there. And then what you do at the end was not relevant as we thought about networking. So it made sense to have one network to do this. It also, we could not afford it. There was really no businesses at the early days of networking that could justify building a network. There's no money in it. So we needed economies of scale. So we needed one thing to do to have that. So anyway, it makes sense if you think about it, right? Again, as a local optimum, it makes sense. But it had many effects. So I'll give you one of the effects. One of them is that it stifled innovation. So I remember, and there's a little bit left over, and I don't know if people felt it here that have been around for a while. You couldn't go out and propose new things because the first thing they would ask you, is it deployable on the current internet? And if it was not, they would say, we are not interested in it because what is the point? You could innovate as much as you want, but if you can't take it to practice, who cares? Why are we going to put, taxpayers' money to help you do this kind of research? So this was bad. The other thing is, if you thought of anything that would work on a small scale, no one was interested. They said that the network has millions of users. You're proposing something, it's not going to work for millions of users. But even if you're saying it could, you cannot prove it. How are you going to prove it? How are you going to prove something works for millions of users? Well, you cannot, because you're giving me money for 5 machines in my lab. This is all I can prove. So basically, it was very difficult to validate anything. Even if you could say this is deployable on the internet and scalable, you couldn't prove it. So people started thinking, well, here's how we're going to let you prove it. We're going to build all of these experimentation environments to let you prove it. And these are the ones I could think of: M-Bone for Multicast, Q-Bone for quality of service, 6-Bone for IP version 6, then more generic ones, Planet Lab, and today's Genie. None of them, I will argue, really succeeded in giving us an experimentation environment that could validate stuff at scale, which is really the purpose of that. So in fact, I think this one network really hurt us as networking researchers because it kind of focused our creativity into a very narrow kind of tunnel. Now, The other thing, of course, is that one network is what led to ossification. If you think about it, if we had many networks, if we kept this many networks world with all this listing, you would not ossify because you could always build a new network to do something else, right? So by definition, many networks cannot ossify because you can always just add one more network. And the one network really is kind of the inevitable, leading us inevitably to ossification. Okay, so now it seems like I painted a really bad picture here. That basically we have one network and it's ossified, so we should all go home, right? I mean, no reason to do any more work. There is actually something that is happening now in the last few years that's actually giving us hope, I think, and more than that, excitement. And that is that I believe, now from now on, I'm kind of more into the projection and into the future. The one network is fragmenting, and I'll explain what's going on. And basically, I think we're seeing exactly the opposite now of what we saw before. We're going to see one network that does everything fragment into many networks now that each specialize for certain things. Like I said, this is about future. I realize this Yogi Berra is a famous baseball coach, but he has, if you go online, he's got these fancy, very funny quotes, but one of them is, it's tough to make predictions, especially about the future. And this is what I'm trying to do now. So just take it with a grain of salt or question it if you like, okay? Okay, so here is, you remember this picture. So what is going on is that we now have an unstoppable force that is this demand on the network, right? The demand on the network is going to keep increasing in scale and services. Things that we're doing today could not have been conceived of 20, 30 years ago. And the scale that we're seeing today, again, could not, no matter how you look at any predictions from 20, 30 years ago in terms of numbers, nothing comes close to the numbers we're seeing now. So what happens when this unstoppable force, which is the new demands on the network, meets the ossified immovable object, which is the internet? What happens, right? So what happens, of course, this is one of these philosophical questions that you would ask. In this case, actually, the answer is simple. The unstoppable force will win. And the reason is that, if nothing else, there's a lot of money behind it. There is now business models that are willing to pump in a lot of dollars, a lot of euros into services and into infrastructure. So, like I said, the ossified internet is yielding, it's breaking up, and we're going to probably see a return to ManyNets. Again, I'll leave that with a question mark, but I'll show you the early signs. So here's some early signs. The first question I will ask you, and that actually some people, so if you use Google, and actually, I wouldn't know exactly how it works here, but I suspect something similar. The question is, are you using the internet if you use Google? So some people say, well, of course you are using this. By definition, Google is the internet, right? But let me argue for it. So this is, and forgive me if you're not a geeky network person, but this is something called traceroute. Basically, you can sit in some place and figure out what is the path that you're taking in the network to some other place. So I did this. This is from Georgia Tech. And this is a listing of the locations you visit from Georgia Tech all the way to Google. And what you find is that basically there are a few routers here that are Georgia Tech, and then from the 74 number here on is all Google, inside Google's network. So basically I hop a few routers, probably around my lab somewhere, and now I'm into the Google network. This big 70,000 node network that I showed you is completely gone. It's just very simple. So in terms of the network, it's very simple. The other thing that you see is Google actually stopped using for its own services the traditional TCP and HTTP protocols that run the web and run the transport in the network. They use something called QUIC, and you can see this by running something on. If you're using Chrome and you're going Google, you're actually not using HTTP or TCP, which are, if you think about it by definition, that's the internet. So you're not using those anymore. Furthermore, Google Fiber is now defunct, but for a while, Google was actually giving us a network even to my home. So they had I think they stopped the rollout in Atlanta. They have it in a few places. But you could be in your apartment connected to a Google network that then goes to YouTube, which is owned by Google Network, and then you're using their Quick protocol and their Chrome browser. And so basically everything we teach in my class about networking is gone. It's not there. I mean, we don't teach Quick. We don't teach, I don't actually know exactly what they're doing in their network. So everything about the internet is gone. So there are contexts where if you're using Google, the internet has disappeared completely, right? So this is a totally separate network with totally separate technology. And the reason it's happening here is because Google can afford it, right? Not everyone can do it, but Google has a lot of money and a lot of incentive to do this. So I'll give you another, how are we doing on time? Let me skip some things here because I think, we're doing okay? Okay, all right, so let me tell you that basically the network today used to be, remember, that was about bit pipes trying to get you from here to there. Now we're not about that. The internet now is, the big incentive for the network is content delivery. This is where the money is, the video streaming and other kinds of content delivery, okay? And for those, the content provider cares a lot. So Netflix, Google, Amazon, all these people, they care a lot about how you as a customer perceive them. And they don't want anyone between you and them, okay? Because that means lost revenue for them. So they want to reduce the reliance on anything in between that they cannot control. The old days, this is what the network would look like. This is you buying service from your internet service provider. Then the content provider buys service from its own service provider, and then to go from you to them, you have to go over the network. Slowly, though, the content providers decided, okay, we're not going to put up with that. We're going to do this direct connection called the peering link between us and your ISP. So now you at least go directly from, this is what you saw on the trace route, this would be Georgia Tech, and this would be the Google network. And increasingly, this is what the network looks like. Basically, it's you and your access ISP, and all the important people you talk to, all the ones that you subscribe to, anyone you pay money to, is connected directly to you. And it actually doesn't matter where you are, because these providers have a presence everywhere. Netflix will connect to people here, to people in the US, in various states, and so on. So it's always like this. Now, increasingly, though, what's happening is this is not good enough, because this access ISP now can completely demolish the experience that you see as a user. And so what they're doing is adding things inside the access ISP that belongs to the content provider, including servers. So Netflix, for example, will provide servers that you can put inside your access ISP to serve customers, so you would never have to leave and go anywhere else. And in fact, the picture starts looking something like this, where your end user basically looks like it's connected to the access ISP, but actually there are some special services going on here that you're almost directly connected to your content provider. And this is what I've been calling zero-hop network. Okay, basically you go directly from you to the content provider. Now, so this is what's happening in the internet. Some people, though, are saying this is not good enough for us. We need to build our own network to do what we need. And you're seeing slowly a little bit of this happening. And here are some examples. One of the earliest was something called spread networks. This is for stock trading. They wanted, this was really a link from New York to Chicago, that they wanted sub 10 millisecond latency just so that the stock trades are acting on accurate information or up-to-date information. So they said, forget about the internet. They built their own fiber, own applications, everything, no internet in between. Basically, they called it ultra-low latency service. Sigfox, who I'm not sure they made it here, but this is really a French startup that is in a lot of places in Europe with very good coverage. For Internet of Things signaling, you don't need very high bandwidths, and you really don't need all the burden of TCP and IP and so on. So they built their own network. They rode over cell towers, unlicensed spectrum usage, and developed both ends, the client and the server. Everything is theirs. The protocols are different, and they basically run from one end to the other completely on the side, no internet in between. So again, this is a bypass network. It's a network that people have spent money building, run applications on that does not use the internet. Another one, and I have to be careful, some of these things come and go. This is a startup. Spread Networks and Sigfox have been around for a while. Haste is a startup, I think it's still around. Basically, this is for gamers, again, that require very low latency in their games, so you can subscribe to them. I don't know that they have presence everywhere, but basically they built, it's very hard to know exactly what they did. Everything is proprietary, but you could tell that they bought their own routers, built their own network. You connect directly to them, and they connect directly to the game server, so everything runs very fast. And you, of course, pay them to do it. FirstNet is a network in the US for first responders. Again, running first responder traffic on, these are people that run emergency services, fire, ambulance, police, and so on. You don't want them to run on the internet with the delays and the bandwidth unpredictability, so they built their own network. Okay. So you're beginning to see pieces of this happening, and everyone is one, and everyone you can make an argument for, but maybe we'll keep seeing more and more of this. In the future, I think we're talking about 5G and 5G slicing. If you look at the 5G literature, this is kind of the future of mobile communication. You will see people already talking about different types of networks, one for high bandwidth, one for low latency, and one for scale. This is for Internet of Things, massive machine type communications. A bit fuzzy concept, but basically, if you look at some of this is from Huawei's literature, you will see basically they're talking about different networks essentially doing different things. Okay, they're riding on the same hardware perhaps, but at least conceptually you're thinking of this as 3 separate networks for 3 different applications. Okay, so hopefully I convince you that basically one of the responses to this ossification is this fragmentation. The internet now you're seeing more and more pieces split off from the internet to do different things. I think the question is, so what? So what's what is the conclusion? So first of all, I think the networking community, certainly networking researchers, have not acknowledged this. I get a lot of resistance, and again, I could be wrong, of course, but I think the evidence is clear. But also, I think this idea of a single network to do everything is so ingrained in everything. I think, for example, in the US, when people realized ossification was causing all sorts of problems, the first conclusion was, the network design is wrong, so we're going to build a new network. We're going to define this. They had this clean slate architectures, so they called for proposals. Clean slate meaning throw away everything, build a new network from scratch. And one of the requirements was this network was never to be ossified, that it had to be flexible and so on. There's a lot of intellectual kind of contributions of this effort, but I don't think anyone believes that any of these proposals is going to see the light of day as a deployed infrastructure to replace the internet ever. So this idea of trying to just replace the internet with another single network with just now better technology, I think that has failed, and I don't think that will ever happen. The other thing is that why should we complain? I mean, actually, remember what I told you, that one of the things about the single internet is it was becoming really hard to propose new things because people saying, well, it's not deployable on the single internet, so who cares? So what I'm saying is that it's not a bad idea. Why not? Why not have multiple networks and then open up our creativity to now proposing different networks, maybe think about how we might federate these networks in some fashion so that they're not completely isolated in cases where it's required. In some other cases, there are services today, some of them like the Internet of Things and Sigfox. There are certainly services like video streaming where there's so much money that they can certainly justify lots of their own infrastructure. There is a negative side to this, though. The one network had some advantages. Certainly, economy of scale was one of them. So the question is, for people that can afford it, certainly they can build a different network and use it. The one network gave us this, what people call low barrier to entry. So if you could come up with a new service that you wanted to run, you did not have to build a new network, and you could just ride over the current infrastructure. Again, Netflix is a great example of this, because Netflix, when it started, really didn't have all the facilities that they have today in terms of being able to project into ISPs and all that. They were just running as applications at the end, using whatever the network gave them. As they grew, they were able to do more and more. And certainly true for Google and true for all the other services that are huge today. They could start easily and build in the current network. If we start insisting that everyone build their own network, we have an issue because some services will not see the light of day because you just can't afford to do it. So we have to really kind of keep this one network, or one network where people can ride on for a while or something. I'm not really sure what the model will be, but something to keep this low barrier to entry for new services. Okay, so this is, I'm reaching the end here. So I hope I made it interesting and made it clear that I think it's an exciting future. I think ossification, when people were talking ossified, was actually pretty disheartening and depressing. You walk out of a talk and say, okay, why am I doing anything? Because no matter what I do, no one is going to deploy it because the network is not changing anymore. And in fact, there were some years where the networking agenda dried up, the money dried up, and we were all experiencing this until they tried this clean slate world, which injected some new energy. But again, I think it was, again, hindsight is 2020. It was really trying to do something that was just not doable, which is replace the one network with another one network that would not ossify. I don't see that ever happening. Now, the good news, of course, is that there is no end in sight. I mean, the creativity is going to keep going. The scale is going to keep going. There's going to be new things that we can think of that we never thought of before. And there is really no end in sight to the demands in terms of scale, the number of people that want to connect to the network. And hopefully with this fragmentation, we can't talk about ossification. Like I said, by definition, if you have a world where you can deploy different networks for different things, that world cannot be ossified because you can always do different things. And so we will stop talking about ossification, and it will be fertile ground for new research, I think. Now, you think about, this is something a little bit orthogonal, but certainly hard to ignore today, which is this network programmability is allowing us to think about the difference between network hardware and network software. So these many networks could be, for example, the same set of hardware, but just different programming, right? Different software. And so that will make it easier to understand and maybe easier to justify in some cases. And certainly there's been a lot of effort recently on network programmability in the software-defined network world. Okay, let me repeat the takeaways. This is what I showed you earlier, and hopefully now it makes sense that there is this fundamental process of going through these iterations that even ossification couldn't stop. So once the ossification happened, what happened is the force of demands kind of broke up the network into many pieces, as we are beginning to see. The single network, really, we should not be wedded to that as religion. I think that some people's reaction to my talk is that, well, the single network is something that is fundamental and we need to maintain it for everything. And I really don't think that that's the case anymore. I think that we're already seeing a bunch of many networks showing up for different things, and probably we'll keep seeing more. But again, this is very good. This is something that we should embrace because it will help our future as networking researchers. So thank you very much.
Thank you very much, Professor Ammar. This talk was, I think, touched us very much. We use these tools every day as developers and as users. I found it very, very informative. I have a few questions, but first I'd like to give the audience the first chance to ask, if you have a burning question. Here, please.
Thank you very much for a lovely presentation. I thank for the takeaway messages and for drawing attention to this overlooked milestone in network development. Now, I have have two questions. One would be, so your resistance, detractors, opposition, what do they say against this concept that you foresee from one net to many? What are the arguments against? And maybe you could give a little brief history how this idea came to your mind, how you stumbled upon it, some historical reason, or maybe it was somebody else's idea that you took away and further developed.
Okay, so let me answer the first question. So the resistance I get, to be honest, I mean, I should be fair that as with anything, I question some of this myself, because I'm always talking about the future and who knows what will happen. But I think as growing up as, in classes and everything, no one really talks about anything except the internet and classes that were the 87 class or the 89 class that I used to teach, this is how SNA did it, this is how, DECnet did it and all that. We're not being taught like that. And in fact, I don't teach like that anymore. And so, growing up as students, we believe in this one network. And it actually, as a concept, it's not a bad thing. It's like thinking, if you watch Star Trek, United Federation of Planets, okay? I mean, we're having a hard time getting United States of America now. So I think as a concept, it's a great thing, right? It's a great thing. But I think so that's why I think people resist it, because it's kind of this utopic thing that is great to have. I think once you kind of, you look at it and you see that maybe it's hurting us in a number of ways. I should also say that the idea of ossification itself is controversial. So there are people that believe that there is no such thing, that the network continues to develop, that in detail, of course, it continues to develop. We didn't have fiber today, and so we have fiber today. So at some level, actually, below the physical layer, things keep moving very fast. So some people believe there is no ossification. And so the fact that the cycle will keep going, you don't need to break anything up. So that's part of the resistance.
From an evolutionary perspective, I think ossification is not even the right term, because it means, it's death. Something gets like a developed arm.
Yeah.
So this maybe was just a stage of some sort of dormant sporulation or something. Okay, and so the second about history. I did a lot of work on multicast in my previous life. So I spent many years thinking about multicast, and I had another talk that talks about why multicast basically failed. And one of the things I argued for, and although not in exact same words, was basically that we anticipated things. We tried to build multicast for a network 20 years from now, and so never got experience. And so this is how the whole idea started in my mind when thinking about why multicast really failed to see deployment. And so I was giving a talk like that, and actually I had a talk that I had like in another dimension, what would have happened if, for example, Aguilar's proposal in '84 was taken and deployed in the network? What would have happened, and how multicast would have been with us all the time? So this is really the genesis of the idea, and then I started, thinking about it in more general terms. All right, it evolved. It was not a eureka moment.
No. It was over time. Yeah, over time.
Thank you very much.
Thank you.
Just one comment on this ossification when you talk about ManyNets. Do you foresee that in the future these ManyNets might be like many silos, where it's like each silo of one silo for Google, one silo for Microsoft, or one of these big players as such? And that might result in some kind of stagnation of the research, because it's like unless you're collaborating with Google, we won't be able to get anything published.
Yeah, I mean, so the question is there going to be silos for different companies? And, to some degree we're seeing this in, I don't want to pick on Google, but Google basically is large enough that they basically have they do their own thing, right? And you cannot actually study their networks without collaborating with them. They have the data and they have these kinds of things. So I can see advantages for these companies not to build a silo, to actually, because some of them are large enough that they can generate their own kind of ideas internally and build things. But I think over time, even the big companies become kind of more, everything is inside. And so it's very hard then to feed new ideas from outside. So I can see where they want to contribute to the world. So I'll give you an example. The Google Quick, for example, is really something that they run with. They have it. However, they are trying to push it as a standard in the IETF. They are, actually, there's an open source version of it, because you can't actually see what they actually do, but they have open source versions of it for students, for researchers to work with. So they are trying to, even though it's something they're doing for themselves, they're trying to open it up. So I can see that people will continue to be open to talking about what they're doing.
We have other questions. If no burning question, I suggest we would continue the discussion outside. I hope there is our refreshments and drinks. So I invite everybody to join us and continue the discussion. Thank you very much.
Thank you.
Great talk.